Hello and welcome to Simple DC Circuits. In this video, I'll cover a general overview of the basic behaviors and rules of series and parallel circuits and hopefully provide you with some insight on how these circuits can operate in modern day applications. So let's begin. Now, the biggest thing that you need to remember is Ohm's law, which is voltage is equal to current times the resistance. And the other thing that you need to know is the power rules. And there's two of them actually. So power can equal current times the voltage, or power is equal to the current squared times the resistance. Now throughout this video, I'll keep referring back to these formulas. And it is important to note that these formulas will hold true for any DC circuit. So it's very important to remember these. So let's move on to our first example, which is a series circuit. And in this circuit, you can see that there's a 5-volt supply. There is resistor 1, which is equal to 1 ohm. And there's resistor 2, which is equal to 2 ohms. Now, the first thing I like to do when calculating the results of this circuit is to first find the equivalent resistance. So, the equivalent resistance in this case is the total resistance is equal to R1, resistor 1, plus R2, resistor 2. And we know that R1 is equal to 1 ohm, and R2 is equal to 2 ohms. So in total, we have 3 ohms, or the equivalent resistance is 3 ohms. Now, it's important to note here that the current in a series circuit will always be the same. And that means that the current here will be the same as the current here, and also the same as the current here. So the current doesn't change throughout the entire circuit. Okay? So now if we go back and we remember what Ohm's law is, so V equals IR, IR, or voltage equals current times resistance, we can actually calculate the overall, or the total current in this circuit, because we have the voltage and we have the resistance total, right? So that would be 5 volts equals I times the resistance total, which we just calculated to be 3 ohms. Okay? So if we rearrange this equation, we can get I on its own. So I will then equal 5 volts divided by 3 ohms, which is equal to 1.6667 amps. Okay? So now we know the total current in the circuit. But let's say we want to find out what the voltage that is being supplied in R2 is. Okay, well, it's quite simple. Now that we have the total current, we can just reapply this Ohm's law, and we can actually find out what the voltage is across R2. Same with R1. So if we go R2, so V for R2 is actually just I times R, which is equal to, now we know that the current remains the same in a series circuit, so therefore I must equal to 1.667, and R for R2 is 2 ohms. So it's quite simply 1.6667 times 2 ohms. Okay? Which comes out to be about approximately 3.2 volts. And the same deal for the voltage across R1. VR1 equals I times R1, and I should actually put R2 here so you don't get confused, is equal to 1.6667 times, and we know that R1 is equal to 1 ohm, so it's simply times 1 ohm equals 1.6667 volts. Now we know this can be true because in a series circuit, the sum of all the voltages should equal 5 volts. Now I've approximated this voltage here, so realistically it'd be more like 3.333. So if we go Vt equals the sum of VR1 plus VR2, and I've just noticed I missed the R1 there, we should get 5 volts, right? So voltage R1 we know is 1.6667 volts, plus the voltage on R2, which we said is 3.2, but I have approximated it. 3.2 actually gives us 4.8667 volts. And I should say, use the correct symbol, is approximately 4.86667. But realistically, it is actually 5 volts. Okay, so hopefully that's given you a quick overview on the Ohm's law of a series circuit. And the same deal, we could apply power rules and whatnot as well to find the wattage across R2 and wattage across R1 by simply using the formula P equals IV or P equals I squared R. And for example, we could say the power in the entire circuit, we will be using the voltage for the entire circuit, and we'll also be using the current for the entire circuit. Okay? So you would just have to go P equals 1.6667 times 5, and then you would get, let me quickly do some quick maths, 8.335 watts. Okay? So we'll move now on to parallel circuits. And it's not exactly the same. Finding the equivalent resistance in this circuit is a little bit different. It's not as simple as series circuits. So again, I like to start off with finding the equivalent resistance. In which case, in parallel circuits, is actually 1 over RT is equal to 1 over R1 plus 1 over R2. Okay? So we still have a 5 volt supply, and our R1 is still 1 ohm, and our R2 is 2 ohms. So the parameters don't change. However, the formula does. So 1 over RT will then equal 1 over 1 plus 1 over 2, which is actually equal to 3 over 2. Now, this isn't 3 over 2 ohms or 1.5 ohms because you still have 1 over RT. Now to find RT, so RT, you'll actually have to do the reciprocal of this, and the reciprocal means just invert it or flip the fraction basically. So RT will then equal 2 over 3, which is equal to 0.6667 ohms. Okay? So Now that we've found the equivalent circuit for these two, the circuit itself will actually look something like this. And that's RT, and that's 5 volts, and this is actually 0.6667 ohms. Now, this circuit now looks like a series circuit. We don't have these two branches, right? So we now can apply the same formulas that we did with the series circuit to our equivalent circuit, which is a series circuit. Makes it much simpler. So if we go ahead and we use Ohm's law again, which is V equals IR, we can actually find out what the total current flowing through here is, okay? Which is the total current. It's current in parallel actually branches off. Oops, my apologies. Oops. Current branches off into two places in this circuit. So current doesn't remain the same in the circuit, but we can find out what the current is flowing through here and flowing back into here. Okay? It will be different. The current will not be the same as there, and it will not be the same there. Okay, but we'll find that out later. For now, we want to find out what this current is. Okay? So voltage, which is 5 volts, so 5 equals I times RT, which equals 5 volts equals I, and what did we say? Times 0.667. So therefore, I, rearranging the equation to get I on its own, I equals 5 divided by 0.6667 ohms. And that equals, oops, 5 divided by 0.6667, we actually have 7.5 amps. And that 7.5 amps is here. 7.5 amps. Okay? And like I said before, there will be a different current going through here and a different current going through here. But the sum of these two currents will equal 7.5 amps. Okay? Alright. So it's important to note that the voltage in a parallel circuit, I better write this down. The voltage in a parallel circuit, oops, I can't spell parallel. Remains the same. Unlike current. So if we went back up to the series circuit, the voltage actually changes throughout the circuit. So the voltage here will be more than the voltage after the first resistor, and it will also be more after the third resistor, or the second resistor, I should say. So the voltage actually decreases over load, or over the resistors. Whereas in a parallel circuit, the voltage is the same at this point, and is also the same at this point. Okay? So we actually know what the overall voltage is, and that's 5 volts. So 5 volts is traveling through R1, and 5 volts is also traveling through R2. Okay? But we just said that the current is different. So it's the same thing. We use Ohm's law. I'll scroll down a little bit. So if we go back to Ohm's law again, so if we want to find the voltage in resistor 1, the current in R1, if we rearrange Ohm's law, we'll have the voltage divided by R1. And the same goes for the current in R2. It's the voltage divided by R2. Okay? Which we have 5 volts divided by R1, which is 1. So therefore we have 5 amps. And the current in R2 is 5 volts divided by 2 ohms. Just put the little ohm symbol there. And that equals 2.5 amps. Now we know this is true because we just calculated the total current for the entire circuit. So we know that we're correct because the sum of all currents, 5 amps plus 2.5 amps equals 7.5 amps. So we know we're right. We know we're right because the sum of our currents in each of our branches equals 7.5 amps. Okay? And that's as simple as it gets. Alright, so now you've calculated the overall current. Okay? And you've also calculated the currents in this branch and the current in this branch, knowing that the voltage remains the same. So then what about power? Well, it's the same deal. You could have P equals IV, and the overall power consumed in this circuit is equal to the total current, which is 7.5 amps. 7.5 amps multiplied by the supply voltage, which is 5 volts. Okay? And that equals 37.5 watts. Okay? Now, there's 2 ways to calculate. Say you wanted to calculate the current through the first resistor. There's 2 ways you could go about it. And this is why I said it's very important to know these 2 formulas. Right? So we've got P equals IV, or power equals current times voltage, and power equals current squared times the resistance. Okay? So say we wanted to use the same formula, power in, say, resistor 1 equals the current flowing through resistor 1 times the voltage. And we now know from before that the current flowing through the resistor 1 is 5 amps. And the voltage, like I said before, the voltage in a parallel circuit remains the same, which is 5 volts. So therefore, the power flowing through the resistor 1, or being consumed by the resistor, I should say, is actually equal to 5 amps multiplied by 5 volts, which equals 25 watts. Okay? Alternatively, if we wanted to use that other formula, which is P equals I squared R, right? We know what the current flowing through resistance 1 is, again, and we also know what the resistance 1 is. So therefore, we could just go 5 amps squared times 1 ohm. Now what's 5 times 5, or 5 squared? That's 25 times 1 ohm is equal to 25 watts. So these 2 are exactly the same. Okay, and we've just proven that. So say we wanted to do the last resistor, which is R2. So what's the power flowing or being consumed by R2? Well, that's quite simple. Power of R2, and for argument's sake, I'm going to use the I squared R rule. So I R2 squared times the resistance for R2. And what's IR2? IR2 is 2.5 amps. So that equals 2.5 squared multiplied by, what was it? 2 ohms. 2 ohms. So we get 12.5 watts. Okay? And the sum of the power coming out from here, or the total circuit I should say, should equal the power being consumed by resistor 1 and resistor 2. So power T should have a different color. Power T, or power total, equals PR1 plus PR2. And I should actually put PT up here as well. So the power total, which we did calculate before, which is 37.5 watts. So 37.5, that is a terrible 7 watts, should equal 25 watts, which is our PR1, plus our PR2, which is 12.5. And that is true. 37.5 watts does in fact equal 37.5 watts. How cool is that? So now you've worked out series circuits. You've also worked out a parallel circuit. But what happens if we have both these series and parallel circuits in the same circuit? So how I would tackle this is I would actually find the equivalent resistance again, but it's a lot easier to work out individual branches. Oops, I shouldn't be using that. Individual branches, the equivalent resistance in individual branches, rather than just the equivalent resistance overall, straight off. So I like to tackle it by working out the series resistance, the equivalent resistance in the series circuit, and then we'll have one resistance in this branch, and then we'll have a parallel circuit, so then we can find the equivalent resistance in both. So let me explain that a little bit easier to you. So we want to find, let's call this branch 1, and we'll call this branch 2. So we want to find the equivalent resistance, or resistance, in branch 1. So we'll say branch 1. And this is a series circuit. Branch 1 is a series circuit. So it is simple as R2 plus R3, which equals 2 ohms plus 3 ohms. And that equals 5 ohms. Okay? So now we just have a similar parallel circuit like we did before. And that is equal to 5 ohms. And that is still equal to 1 ohm. And we've got branch 1. And we've got R1. Okay? So now we need to find out what the equivalent resistance of this circuit is. And that is the same method as we did before, up here. Okay? So we'll be using this formula, or I should say this one, 1 over RT equals 1 over R1 plus 1 over R2. Because now it looks exactly like this. So I'll go ahead and start that. So 1 over RT is equal to 1 over R1 plus, I'm going to say for R2 is actually 1 over R branch 1 1 over R branch 1. And let me extend that a little bit further. I'll make that look prettier actually. There we go. So that is equal to 1 over 1 plus 1 over 5 ohms and ohms. Okay? Which equals 6 over 5 ohms. But if you remember again, we need to find RT, we'll need to flip this fraction, which is called finding the reciprocal. So RT, actually equals 5 over 6 ohms, which equals 0.8333 ohms. Okay? Now we have found the equivalent resistance of this circuit. So essentially what you've done now is shorten the circuit again. So you've just got that. It's a terrible drawing, but you've got 5 volts there and you've got 0.8333 ohms there. How easy is it to work out the overall current now? Well, again, we just apply Ohm's law. V equals IR, which equals, or should I rearrange? I should rearrange first. I equals V divided by R, which equals 5 volts divided by 0.8333. And doing some quick maths, we get approximately 6 amps. Okay? So now we know that we have 6 amps flowing through there. But we need to know what current is flowing through there and what current is flowing through there. Okay? So if we apply our parallel rule before that we were talking about, where voltage in a parallel circuit remains the same, we can actually work out what the current flowing through R1 is. Because the voltage is the same for here, it's also the same for here. Okay? So we'll work out what the current flowing through R1 first off is. So let me go back to this. So I R1 is equal to V divided by R1. And what I've just done here is rearranged Ohm's law. So instead of V equals IR, I move the R over to the V, and you get I equals V on R. So if I go back to this, we know what V is because it remains the same, so that's 5 volts, that's the supply voltage, divided by R1, which is 1 ohm. So 1 ohm, and that equals 5 amps. Okay, so we could do a little cheat here, and we know that the sum of all currents, so the sum of all currents flowing out must be the sum of currents flowing, out. Okay, so we have 6 amps here, and now we know that there's 5 amps flowing into here. So we could immediately say, well, what's 6 to minus 5, and that's 1 amp, without even having to do the calculations. And we know that current remains the same through a series circuit. So the current doesn't change over R3, nor does it change over R2. Okay? But the voltage does. The voltage changes through R3 and the voltage changes through R2. So we can say that, let me get my correct color out, I branch, and what we'd say, branch 1, this is branch 1, the bottom one is branch 1. So I branch 1 is equal to the voltage divided by, oops, what am I doing? Not I branch 1, I want to find out the voltage. So the voltage in branch 1, oops, oh, it's not even in branch 1. My apologies, it's the voltage across R3 that we're trying to find. And we know that it's I branch 1, that's better, times the resistance, or R3, because we're trying to find what the voltage flowing through R3 is. And that is equal to 1 amp times, what was it, 3 ohms. 3 ohms. That must equal 3 volts. Okay? So what's the voltage across R2? That's the same deal. I branch, oops, 1 times R2. And that equals 1 amp, current doesn't change, times 2 ohms, equals 2 volts. And we know that this is true because if you sum them together, you'll have the supply voltage. So the voltage across R3 plus the voltage across R2 should equal the sum of all voltages, which is 5 volts. So 3 volts plus 2 volts equals 5 volts. So we know that we're right. We know that there is in fact 1 amp flowing through branch 1. And we now know that there's 3 volts in R3 and there's 2 volts in R2. So we've calculated both current and voltage in this entire circuit. By first simplifying or finding the equivalent resistance, we summed the bottom branch resistances together because they are in series, and we got 5 ohms. And then we were left with this circuit. And then we just had to apply our parallel rules, which is 1 over RT equals 1 over R1 plus 1 over R2, etc., etc. And we've got 5 over 6 ohms, or 0.8333 ohms. And we were left with this circuit, which is our equivalent circuit. And then we could find out what the total current was for this circuit, which was 6 amps, by using Ohm's law. So from there, we could then find out what the current flowing into this branch is and what the current flowing into this branch is. Because we knew what the resistance was in R1, and the voltage in a parallel circuit doesn't change. It only changes in a series circuit. So we found out that the current through R1 was actually 5 amps. And we did a bit of a cheat because we knew that the overall current, the total current for this circuit was 6 amps. So therefore, the current flowing through this branch had to be 6 amps minus 5 amps. So we knew that there was going to be 1 amp. Now we could calculate that if we wanted to. We could say that the equivalent resistance in this branch is 5 ohms. And we know that because we calculated that before, up here. Okay? And then all we need to do is apply Ohm's law, is V equals IR. And the current through that branch is I over V divided by R. And we know that voltage is the same, so 5 volts divided by the equivalent resistance, which was 5 ohms, which equals 1 amp. So we are right. We know that 1 amp was flowing through this part of the circuit. So what if we wanted to calculate power? It's the same rules as before. Okay? P equals IV. And the power in the total circuit is equal to the current in the total circuit, which we know is 6 amps. 6 amps multiplied by the supply voltage, which is 5 volts. And that equals 30 watts. Now I can leave it for you guys as an exercise to calculate what the power in this resistance is, and the power in this resistance, and the power in this resistance, or the power in the equivalent resistance for this circuit. I'll leave that for an exercise for you guys. Just remember, you can use P equals IV, or P equals I squared R. So finally, we're going to move on to, well, how does solar power, or how does these DC circuits help us with modern day applications? And one brilliant example of this is solar power. Solar power, so what is solar power? Solar power, it absorbs the light and converts that into electricity. A potential difference, I should say. So what is solar power? It converts a light source into a power source. That's the simplest explanation I can give. And what is this? So a power source, and you were just shown a power source before, was a battery, right? This is a battery or a power source. So positive, minus, okay? So instead of using this, it's exactly the same, but we're just considering solar power as our power source, okay? So how can we use it? It's exactly the same. You have, in a solar panel, you have many arrays, or many cells I should say. That's 1 cell, that's 2 cell, that's 3 cell, that's 4 cell, that's 5 cell, 6 cell, and so on, okay? And these cells here would be all tied in series. And these cells here, the ones that go from top to bottom, would be all tied in parallel. So what you would have is technically, how's that? Okay, they're tied together. And then we would also have, so they're in series, and then you'd have these in parallel. Okay? And then you could have whatever you want down the bottom. You could have as your load. Or in our case, would be a resistor. Alright? So that's positive, that's negative. So how do we calculate using solar power? Well, solar power, and I might just quickly move this off to the side. Solar power is generally given in a wattage and also a voltage. That's the description of them. So off the shelf, they would say this solar panel provides 100 watts at 12 volts DC. Meaning that at optimal conditions, this solar panel will produce 100 watts of power at 12 volts DC. Power equals IV, and the current for this solar panel up here would be 100 watts divided by 12, which would equal 8.333 amps. Okay. So let me see if I can draw this in a little bit better for you guys. So this section here, oops, that didn't quite come out the way I wanted it to, but it will work. That section there will actually produce 100 watts at 12 volts DC. Oops. Okay. So how do we calculate what each cell could produce? Well, each cell, say there is only one, what have we got? We've got 1, 2, 3, 4, and then 1, 2, 3, 4. So we've got 4 in series, and then we've got only 2 branches for parallel. So 4 in series, and we know that in series, you add the voltages together because current remains the same. And then in parallel, you would add the currents together because the voltage remains the same. So in series, we know that we get 12 volts DC out. So 12 volts DC per cell, which is 12 volts DC divided by 4 cells actually equals 3 volts per cell. Okay? And we calculated before what the current is because it produces 100 watts at 12 volts DC. So we know that the current is 8.33 amps. And current is shared between these 2 branches, right? So therefore, because these 2 branches are the same, they've got the same amount of cells in each, we could simply just divide the overall current by 2 because we've got 2 branches, and then you'd have your current per branch. So if we do that, we got 8.333 amps in total. Divide that by 2 branches, or 2 paths that the current can travel. Oops. We would then get 4.15 for argument's sake. Okay, 4.15 amps. But that means that you have 4.15 amps flowing from here to here. Okay? So keep that in mind. Sweet. All right. Well, I think that's all I can teach you for today. You have learnt about the main formulas that you need to know, which is voltage, Ohm's law, voltage equals current times resistance, and power, which equals current times voltage, or current squared times the resistance. We went through some series circuits, or a series circuit example, where you calculated the equivalent resistance, and then you calculated the voltages across R2 and R1, knowing that the current in a series circuit always remains the same. Then finally you calculated the power in each resistance, and you could either use P equals IV or P equals I squared R. Then we moved on to parallel circuits, where we learnt that to find the equivalent resistance or the total resistance in this circuit, you needed to use the formula 1 over RT equals 1 over R1 plus 1 over R2. And we found out that the total resistance in the circuit was 0.6667 ohms. Then we found out what the total current was in this circuit, which was 7.5 amps using Ohm's law. And then we mentioned that the voltage in a parallel circuit always remains the same through each branch. So the voltage through this is the same as the voltage flowing through here. So we know that 5 volts is at this point, and 5 volts is also at this point because our supply voltage was 5 volts. So then we could find out what the current of each current flowing through R1 and R2. So we had your current through R1, which is equal to 5 amps, and our current through R2, which was equal to 2.5 amps. And we know that that was true because we worked out the total current for the circuit was 7.5 amps. And plussing each of these currents together gave us 7.5 amps. And then again, we worked through the power formulas. So P equals IV, you could use that, or you could use P equals I squared R to find out the total power and the power in individual circuits. Or individual branches, I should say. Then finally we went through a conjoined example problem where you had both series and parallel in the same circuit. So you had series down the bottom, and these were also in parallel with each other. So the easiest way to tackle this was to find the equivalent resistance in a series circuit first, which was this one, and then we found the equivalent resistance in the parallel circuits of them. So we found out that the equivalent resistance in the total circuit was 8.333 ohms, and it would look something like that. We then found out what the total current was for the circuit, which is 6 amps. And then from there, we could also find out what the currents were for each branch. Again, applying parallel rules. So we found out using Ohm's law that the current flowing through the first branch was 5 amps, and then the current flowing through the second branch, and the current flowing through the second branch was just 6 amps minus 5 amps, which gave us 1 amp. And then again, finally, we went through a quick example for the power. And then we moved on to solar power. What can we use DC power for? And that is solar power. And we talked about that there's a battery. It's the same as a battery. It converts a light source into a power source. And then how can we use it? Well, if you join up all of these cells together, you're going to get an output. And in this example, we said that this solar array produces 100 watts at 12 volts DC. Okay? So if we said that this solar panel looked like this, then we could calculate what the total current was using P equals IV. And if the load was at its maximum, it's consuming all of this power. Therefore, P equals IV, and the total current flowing through this circuit would equal 8.333 amps. We then said, well, you have 12 volts flowing through here and 12 volts flowing through there. You have 12 volts and 12 volts. So you're always going to have 12 volts there, and you're always going to have 0 volts there after the load consumes all of the power. So if you have 12 volts DC in a cell or in a module, and we know that we have 4 cells, 1, 2, 3, 4, then we go 12 volts divided by 4 cells equals, it must be 3 volts per cell. So that means that this was, was 3 volts. That's 3 volts. That's 3 volts. That's 3 volts. Okay? And we know, based on our current calculations before, that there was in total 8.33 amps. So what was the overall current, what was the current flowing through this section? Well, that's simple. We've got 2 branches, therefore we must have 4.15 amps, or half of our total current flowing through the top one, and half of our current flowing through this one. So they each come out to be approximately 4.15 amps. And that's how you would calculate and design solar power panels in its simplest form. Okay, I hope this has helped you work through some examples in the future. Good luck, and thank you for attending my video. Goodbye.